in here from last time. While I'm calling roll, maybe you could just, well, let's go around in order maybe, and you can say your name, just one either interesting thing about you or things that people know that you're interested in, that, you know, or particular skills that you bring to this class. Or, you know, I would say one or the other of the bullets would be sufficient. Something that one of your friends would say characterizes you. So let's go around this way, and I'm just going to mark you off the roll sheet, and I can also mark any pronunciation as we go. And then we can try the people zooming in too. I'm not sure how well the audio will work there, but at least I'll be able to hear it. Hopefully I can get the audio coming in through the speakers so that everyone will be able to hear at least the folks who are on Zoom. All right, you want to begin?
My name is Hannah Jackson, and I would say one word that a friend would describe me as is competitive.
Competitive, okay. Jackson, here we go, okay. All right, go ahead.
I'm Jesse Schrader. I'm from Knoxville, and one word, say either friendly or bad singer.
What was the second one?
A bad singer.
A bad singer. Oh, okay. Interesting. Maybe we'll get to hear that this term. All right. Yeah.
I'm Everett. One word energetic.
Everett and Hauser. There we go. Right. Thank you. Energetic. That'll be good for us this term. How about in the back corner?
Hi there. My name is Spencer Keegan. I guess one word would be relaxed.
Okay. Great.
I'm Joseph Warner, and one word would be swaggy.
Did you say S-L-A-G-G-Y?
S-W-A-G.
Oh, swaggy. Okay, I was going to say I've never heard the word slaggy before. As far as I know, slag is something that is a byproduct of the smelting process when you're purifying metal, and it's like that leftover stuff at the bottom. So I was curious what that would be. All right, how about you?
My name is Jack Thacker.
Thacker.
Walking around campus.
Sounds good. I always like, you know, there's a stereotype among older people like me of, you know, because I grew up outside the world of cell phones and that everybody's using their devices now. And so, you know, occasionally you'll see a student just walking around, looking around at things or deep in thought from their latest philosophy class. That's always a fun thing to see. All right, let's keep going in the back there. Laid back, okay. Smith. So, oh, here we go. I was going to say you're not on here, but you are. Okay, how about you?
My name is Nick Whitehouse, and I guess my friend would say I'm reliable.
Okay. Go ahead.
I'm Colby Kinzer. I guess my friend would say that I'm quiet.
Okay, Kinzer, yeah, there we go. Quiet, well, we'll have to get you out of your shell since we'll be doing discussion, especially in Dr. Kadavid's class. I mean, it's largely discussion-based, but, and let's see. So I have Reed here. You want to introduce yourself, Reed?
Yeah.
Here we go.
Reed Williams. I guess one word people would use to describe me is honest.
Okay. Now let's see. I think I'm missing someone, or maybe, oh no, Royce did join. That's great. All right, let's just test the audio with those of you who are on there. I assume Uchiri just disappeared again, and maybe his internet is a little bit sketchy. But Chen, you want to say a few words about yourself? I know Chen
Yes.
from a previous physics course.
Yes, sure. My name is Chen, and
I feel really interesting in Einstein's theory, so I choose this class. And I also interested in physics, and my friends would say see me as a smart person somehow, but I don't really think I'm a smart person.
You've just fooled everyone very well. Okay, thanks, Chen. And how about next, Jacob? You want to unmute for a second?
Hi, my name is Jacob Camacho. I guess my friends would describe me as being very respectful and determined.
Respectful and determined. Okay, great. And Royce, you want to say a few words?
Yeah, my name's Royce Pope. I play soccer and I play guitar, and I don't know how a friend would describe me because that's their own opinion.
Yeah. Okay. And finally, Muchiri, you want to see if your audio comes through too?
Hi, my name is Mushiri, a freshman from Kenya, and I'm ambidextrous. I can use both hands perfectly.
Well,
And
I hope you
one
get
or
a
two words
chance
my
to use
friends will
them both.
describe me. Hopefully.
Hopefully. Okay, thanks, Muchiri.
Yeah.
And so Jacob Walterman is not here. So we'll put a question mark by him. I think someone else may have left the course roster this morning, but we'll figure that out later. What I'm going to do first is just go through the syllabus, so that if you're zooming in, you can take out your copy of the syllabus. And just to kind of orient you. And after doing that, in whatever time we have left, we'll talk about the conceptions of space and time that we might bring into this course, and maybe some more ancient conceptions of space and time that I suspect most of us don't come in with anymore, but at one point in history, they were more compelling just based on what people knew at the time. Okay, so let me go forward here. My name is Jim Kelly. I'm a physics professor here, and I'm super excited to be teaching this course. We've done this pair of courses once before, and it worked really, really well. Awesome just to hear the different voices from around campus, not just from a couple of physics interested people and some philosophy majors I've seen in the roster, but also we've had a great diversity of different majors take the course last time, and quite a few first years. I think last time we had 5 or 6 first years in the course. So everybody, it's a great way to have a conversation about some of these concepts we're going to be touching. My office, I'm normally a resident of Olin Hall, and so I'm in Lamott Hall in the basement temporarily now. The spaces are kind of cramped down there, so I'm going to be holding office hours in here, in this room, right after class, and my intention is every single day. That way we can stay spaced out, and the people who are zooming in can just stay on Zoom if they want to ask questions in office hours. The only thing I ask about office hours is that you don't leave and then try to come back later, because just for my own personal efficiency, since I can't work in here as well as I can work in my office, as soon as everyone's sort of gone from the office hours meetings, I'm going to take off, and then the next office hour will be the next class day. So every day after class, if you have questions about the homework we've gotten into, or just general questions about what we've been talking about or connections between the two courses, hang out right after class. Dr. Katavid's class starts at 1:40. What is it?
So we start at 12:45.
12:45, yes, 12:45. Yeah. So we've got a full, if we go till 11 o'clock in here, we've got a full hour and 45 minutes before the other one. So I figured that has enough time for us to have some office hours and go get lunch at the same time. It seemed like the best way to do office hours so that everyone could be in the same place. Email and phone is there. I wouldn't necessarily recommend calling on the phone unless you're sure that I'm going to be in there. So if you want to communicate with me, email is usually the best way. I'm not a late night email reader person. So if you email me at 7 or after, I'll probably respond to it the next morning. I'm not up reading email late at night. The course website is not a Moodle site. So some of you probably, unless you've had me before, may not have had a Google site. So the address was on there. You'll see it again in just a second. When you go to that address, so it's sites.google.com/a/center.edu. And when you go there for the first time, it will ask you to sign in through Center College with your usual ID username that you use at Center. So it's doing the same thing. I've never been on this computer before, so it doesn't know here. Oh, but I have logged in to this system, so I don't have to do it. But, you know, your usual login process. And when you go there, you should see a list of courses that you're a member of. And in all likelihood, you'll just see one of them, which is my course. So of course, I put all my courses on here. So here are lots of instances, but this is us, Physics 165, Fall 2020, Space-Time and Relativity. So you'll click on that course name, and this is what you will see here. There are 3 columns, and perhaps the most important column is the one on the right-hand side, because it's going to govern our daily schedule. I know it's a little bit small to see, at least for those of you in the class here, but what this is date by date. You can, let me see if I can adjust the font size. Does this work? Yeah, there we go. Let's make this bigger too. So I've got, I'm not sure why I have, week 7 is just finals week. Yeah, so we're 6 weeks long since we're starting on a Monday. So week 1 through week 6, and they're going to go upwards because there's going to be a lot of material posted on this, and I always wanted the newest stuff to appear at the top. So these are sort of compressed because there's nothing posted in the later weeks right now. I've only sort of populated the 5 days of this week. So we've got Monday through Friday. Let's go down and look at today's action item. So we're going to have a class meeting discussing the course. That's what we're doing now. And you're supposed to read chapter 1 of Merman's book. That's also on the syllabus, but we may as well show it now. Yours may look a little bit different than this, but mine has a big red dot on the cover. Probably depends on whether you got the paperback edition or not. But it's an old book. It's out of print, but it was sort of the best book at the level, elementary level, that I wanted to teach this course, because you can get more advanced mathematical presentations that presuppose calculus. This one is not that way. And it's, you know, the chapters are nice and short and sweet. That doesn't mean they're going to be an easy read, because they're challenging basic assumptions that we make about space and time. But that's the book. So the idea is today you are supposed to read chapter 1, which is only a few pages long. It's probably 5 or 6 pages. And then you're going to be posting reading responses, and I'll talk about those in just a second. But the reading response links are over here in the first column. And by the way, when you go to this site on your smartphone, you'll just see one continuous column with the first stuff on the left appearing first. And if you scroll down, you'll see the second column. And if you scroll down, you'll see the third column. That's why I put the long column last, so that you don't have to look at all that stuff at the bottom. Okay, and you'll see this week we're going to start having homework problems. Those will be related to things that we're sort of practicing doing during class and whatnot. So you can take a look at those starting in tomorrow's class, where we'll do a first few kinds of problems in class, and there's some related homework problems. In the middle column is where I'm going to populate solutions, mostly to things. They're just things that are of general interest throughout the semester. So the syllabus is up there. If you lose your copy of the syllabus, just go there to the website and check that out. And I have tried to put right now, I think there's only 2 emails in here. Every time I send a substantial class email with some interesting content in it that you may want to reference later in the term, I just plunk the text in here, and they're sort of getting older as they go down. So here's one. If you've been in the course for a long time, you saw this email from me earlier in the summer, and then the one I sent just the other day about today is here. I didn't send the one I didn't put the one in here from yesterday yet, but I probably will because it has the meeting ID in it, just in case you forget that. For you non-Zoom folks, you may all of a sudden find yourself having to zoom in. Okay, let's go back to the stuff on the syllabus now, and we'll go and talk through a few more of those things on the website as we get to them. So yes, that's the course website, the textbook we talked about. You need some kind of calculator for this course. We're going to be calculating things, numbers, intervals in time, or how far away things are, how long objects are. And so you need a calculator. You don't necessarily need a high-powered one. I've got one of these old-fashioned that used to be standard issue high school kind of calculators, the TI series, the most bare bones one. This one's a TI 83 Plus. But many of you will have things like this that you have left over from high school. But that's not to say you even need something like this. We won't be using, I don't think, the graphing capabilities of this calculator. So as long as you can do, there'll be one place where we use one trigonometric function. So, that's not going to be a major emphasis, but there's one case where we will need to hit that tangent or inverse tangent function. So you need to have trigonometry, which is a standard part of most calculators, but you need to be able to take square roots and squares and things like that. And it's not going to get too much more complicated than that. If you're unsure about your calculator, certainly come ask me about it. There are lots of good choices. These TI ones I mentioned on here are certainly not required. They're just the most common ones that we see with students in the US. Okay, moving further down, the course overview. So I'm going to try to just kind of summarize and maybe elaborate on a few things in here. The primary subject of this course is called the special theory of relativity. And so we're going to be talking about that work by Einstein, which is a subset of his rather large collection of work that he did in physics. And it'll be supplemented by a little bit of information about Newton's view of the universe. But we're not going to spend a great deal of time on Newton, and I believe Dr. Katavid's class will spend much more time talking about Newton's ideas than we will in this class. I think the idea for me is that we need all of the time we have to kind of grapple with Einstein's ideas. And we're going to take the point of view that by virtue of being modern citizens, we've grown up with an idea about space and time that more or less tends to match what Newton believes. Now that wasn't always the case in history, but by virtue of being modern citizens, we tend to have been exposed to these ideas. I'll survey you more later on in the class today about how you think about space and time. Special relativity. This word special is in contrast to the general theory of relativity. And sometimes when people hear about special and general relativity, they think the special one is called special because it's more special. But that's not true. It's special in the case of if you have specialized knowledge versus more generalized knowledge. I'd prefer to have the more generalized knowledge because it means it applies to more different cases. So the general theory of relativity is a generalization of the special theory. That's not to say the special theory doesn't apply to a great amount of phenomena in the universe. So we're going to be talking about the special theory mostly because it requires very little sophisticated mathematics. You don't really need calculus to understand it. If you can take squares and square roots and solve very simple equations, nothing complicated. I don't think we'll even be using the quadratic formula or any of those things, but everything that most people learned in high school will be sufficient for what is required to understand the arguments that will be made. So I'm assuming no specialized mathematical knowledge, no calculus, no extreme knowledge of, you know, trigonometry and algebra 2, the kind of stuff that you guys took, or at least some equivalent in high school when you were there. But if you are struggling with mathematics, in other words, if there are problem-solving things, a lot of people are really rusty, and I don't anticipate that many of you are in technical kinds of majors or aspire to technical kinds of majors. If it's causing a barrier for you, please let me know, and we'll see how we can work that out, because it's not intended to be a barrier. There's enough of a barrier in the ideas in relativity, which are supposed to challenge our notions about space and time, that we consider more or less intuitive and we use without even thinking about them. In fact, they're built into the way we use our language. And so that's a big challenge for us, because sometimes just the way you frame a problem pre-assumes some conclusion that you're making about space and time. Some assumptions are built into it, and those assumptions are what we're going to call into question in this course. So that's going to take a substantial amount of time and practice to tease out what those assumptions are being made when we say a certain sentence and not falling into those traps in this course. So that's going to be the barrier. The barrier shouldn't be the mathematics, but let me know if you're having trouble with the mathematics that we do. You'll see that in the presentation, a lot of times there's some mathematics used in the book to get to a particular result. I will use some mathematics to explain it on the board, but oftentimes once we've gotten to the result, we're going to concentrate on how to use the result, and you won't be forced to use the mathematics that goes on in understanding where the result came from that you see in the book. But still, it's all algebra that you learned in high school, presumably. And I'm hoping that you find the prospect of challenging your intuitions that may be wrong exciting, and that's what attracted you to this course. So it's not necessarily going to be an easy ride, but it's because we're questioning things that we assume every day. The payoff will definitely be worth it, not only because Einstein's theory is experimentally confirmed over a much wider range of phenomena than Newton's theory, but also because most people who study it, almost everyone who studies it, once you come to the understanding of it, assess it to be more beautiful, more elegant, more satisfying than Newton's view of the universe, even though Newton's is more immediately intuitive to us. I also wanted to just say something, and Dr. Kadavid is free to contradict me on this or add in whatever she wants, something about the difference in emphasis perceived by me between philosophy and physics and a typical philosophy class and a typical physics class. Both philosophy and physics are interested in finding new ways of seeing and understanding the world. And in fact, philosophy and physics at one time in history were the same pursuit. That's why physics used to be called natural philosophy, the philosophy about the world. This class will be fairly typical of a physics class, and a physics class doesn't necessarily feel exactly the same as a philosophy class, despite that connection. We're going to focus on very specific ideas that have passed experimental tests repeatedly over a great period of time. So you might think of the big theories in physics. You know, if you're in an introductory physics course like I've had with Reed before, you're traveling a 6-lane highway that has been constructed over many, many years and has been very well tested and is understood by a great number of people. And you're trying to learn it because it helps you understand how you may have been thinking about things incorrectly in a way that doesn't agree with experiment in your life before that course. So it's going to be no different in this class. Even though the goal of physics is new ideas, the focus is always on just one well-developed idea. And so that idea in this class is going to be the special theory of relativity. We're not going to consider on a day-to-day basis many alternative ideas along the way. The idea is if you can have this new way of thinking overtake your brain. It's going to allow you a way to pry away some of the assumptions that you've brought into the course. And so it is giving you a new way of thinking, but we're not going to, address 20 or 30 different new ways of thinking in a physics course. Now, in my experience in philosophy classes, the quest for finding out about new ideas always stays in the foreground. And so you get exposed to a much greater variety of new ideas about how to approach the world by different thinkers. And instead of it being a 6-lane highway that almost everyone in the field would agree with the ideas that are being presented, many of those ideas can be quite controversial and are not necessarily accepted by all philosophers. So I'm assuming that in Dr. Katavid's class, we're going to see a wide variety of ideas about space and time that are going to challenge different notions, may challenge notions that we're learning about in Einstein's theory. Certainly we'll be challenging lots of notions that are present in Newton's theory, and we'll be challenging a lot of notions that won't even come up in this physics class. And so it's up to you guys to try to make the connection and start the discussion in class. If you want to make a connection between the two, I will do it sometimes, but you're certainly always welcome to start that conversation in here. Okay, so that is to say, in here we're going to be studying mostly one thing, special theory of relativity. All right, back to the syllabus kinds of items here. I've got 3 in-term exams. This is fairly typical for a physics class. If you're not used to physics classes, you may think, oh my God, what's with all these exams? Well, instead of writing so many papers, we're going to take periodic exams, which are going to practice the kinds of things you'll be doing in homework, and we'll be practicing somewhat in class as well. So I'll try to get you well versed on those kinds of things that are going to be tested on the exams, but it's using the basic notions that have been derived in the book and in class time and making sure we understand how to apply them. So we'll do a lot of examples in class, and the homework will be filled with those too. The dates I put tentative because all of us are in the same 2 classes. I kind of know your schedule, and so I'm hoping this is a little bit less tentative than it might have been in block 1 for me. So we'll hope to stick to those dates, but at least I know where everyone's busy, hopefully, and everyone's not. And the final exam's not up for negotiation. Ours is scheduled in the morning on Tuesday of that 7th week. And for you first years now, you know, but I had some people in block 1 who weren't really sure what was going on with the final. It's always in your same meeting room. And so for us, we have a couple meeting rooms, but it's in our normal Monday, Wednesday, Friday meeting room, this room. And in fact, we'll be meeting in here 5 days a week during this time period. The idea being that in physics courses, I've always found it's useful to be repeatedly exposed to the same kinds of ideas rather than have long gaps, which may serve a course where you're doing a lot of reading and writing yourself. Those long gaps can be really helpful. In physics, I found it can be really helpful to meet regularly. So we're going to be meeting 5 days a week. The nominal amount of time, if you average the number of hours we're supposed to meet per week over the 5 days, it should be from about 9:45 to 11 o'clock, I believe. The time slot on the schedule is to 11:15, but that's too much for the amount of time that we're allotted in the course. Okay, so those percentages, all these percentages here should add up to 100%. The exams, oh yeah, that's, sometimes people are shocked. That's a lot of percentages. Well, that's going to be the kind of thing we're practicing over and over again. So that's where the rubber meets the road. Don't be too intimidated by it. I have downgraded the weight of the first exam because especially if you've never taken a physics course before, you may not know what to expect on the first exam. And so that will be a getting to know you exam. And so I put a little bit less percentage there. Those website reading responses, that was on the right-hand side. Okay, well, maybe I'll end the show here and go back to here. That's on the right, sorry, not the right-hand side, the left-hand side over here. So on this side, oh, I can't do my laser pointer on there, I forgot. when it says read Merman chapter 1 and post responses via link at the left, what you do is you've read chapter 1. It's a nice short read. Not too tough, but they'll get a little bit more difficult as they go on. And you click on that, and there is a little preamble here telling you the kinds of things that you should consider when you're making these posts. The idea is that you want to raise issues. They're primarily to either tell me where you're having difficulty understanding some concept that was raised in the reading, or you're welcome to address something that the reading made you think of and you would like to think more about. And both of them help me, they might help your fellow students, because everyone will be able to see everyone's posts on here. So you see, since I'm logged in, here's me, and it says add a comment, and you add a comment, it puts a date and time stamp on there, and then everyone else who's logged in can see those comments. So you can add those comments. I suggest kind of 2 questions or comments or 3 questions or comments per reading section. Some of those can be, you're welcome to respond to people's comments. That's a perfectly legitimate way to contribute, and I would count that as a contribution for that particular day. And maybe we can address more ideas in here. The kind of thing I'm saying I don't want, there are two kinds of areas that I probably don't want. One is a summary of what you read. I don't want a summary. I want to know specific things that are either causing you trouble or piqued your interest, and or maybe they made you think of something that you had read in a story before or something like that. So not a summary, and also not something that says, well, I don't know how he gets from equation 317 to 3.18. Is he squaring the denominator? For 2 reasons. First of all, that's just sort of a boring thing to read off the start. I don't want to read a question like that. But it also makes me go get my book out and I have to read what the context is. Maybe there's a really interesting question in there, but I want you to put it in, frame it in the context of the kinds of words and concepts that are being brought up in that section, rather than citing, it's okay to cite an equation number, but you should try to phrase your question in a more human way rather than just citing an area and just a little technical result. And if you're having trouble with those, I'll be very forgiving at the beginning. Try your best, read this text at the top and try your best to answer them. And if you're having difficulty with it, please let me know. So that's the reading responses on there. Let me go to large mode again here. We got the book. Oh, okay. So that's our website reading responses. It sort of adds up to a small, but if you didn't really do that, that would add up to, a painful little ding on your grade there. So 5% of your grade is a small percentage, but just to encourage you to reflect on the reading as we get to it. Homework and other assignments, 20%. So that means you got to keep up with the homework. I'm giving that large percentage because you're definitely not going to succeed on the exams at all if you don't complete the homework. And so I'm going to regularly collect homework at least once per week, maybe sometimes a couple times per week, just to make sure that nobody gets too far behind. And I expect you to really complete and understand all of those homework problems. So definitely don't come in with the idea that I'm just going to muddle my way through and hope and just turn in a best guess. If you're having trouble and you don't know what's going on, that's when you ought to ask either in the class period or stay after for office hours. So don't be shy about asking for help. In physics classes, you've really got to make sure you understand all the nuts and bolts of those, because those are the kinds of things that are most likely to appear on the exam. Finally, there's going to be some, I see these numbers are slightly different. I adjusted something. In your syllabus, the numbers are slightly different. And the ones in the printed syllabus, which I think are the ones I emailed yesterday, are the correct ones. I forgot I copied this stuff in here. The paradox, so these numbers are just slightly, there's a little bit less emphasis on the exams. The paradox presentations is now up at 8%. That's true in the version of the syllabus that's linked to on the website. It's also, I think, true in the one I emailed out yesterday. So somehow I just grabbed this from an old version of the syllabus. They're almost these numbers, but the paradox presentations are a little bit more. And we'll talk about more of those at a later time, but the idea is you're going to do a group presentation on something that appears very strongly to be paradoxical. In other words, it's almost like a proof that special relativity can't be consistent. It somehow is inconsistent because it leads to paradox, contradiction. But if you have a correct understanding of relativity, these paradoxes can be understood perfectly sensibly as long as you're not bringing your Newtonian assumptions in there. We'll talk about those later on. You really have to have, a good half of the course in place before we have the tools where we can actually understand how to think about those. So I'll talk about those, maybe after week 3 or so. The grades, normally if this were a regular physics class, I would say, well, we'll just stick to a straight scale where 90 and above is the A range, 80 to 90 is the B range. Here, I don't worry too much about that rigid stuff. I'm saying at the bottom, I reserve the right to be more lenient after comparison of your overall work with center's verbal descriptions for grades. So A range is excellent, B range is good, and so on. And if you're ever unsure about where you're standing currently in the course, you're welcome to ask me. The default computation is just according to these percentages, but sometimes people aren't really sure how to use these percentages to calculate what their overall score in the grade is, like as a percentage. So if you're having trouble with that, certainly bring it up and we'll talk about it. For how to read the text, and I'm sorry about this monologue that I'm doing today. This will not be the normal way I hope to conduct class. I'll try to stop us frequently, and because this kind of thing does put me to sleep, but I felt like I should really talk through things in detail on the syllabus the first day. The text, it's a great text. It's very kind of brief. The arguments, I think, are very clear, but that doesn't mean it's an easy thing to read. If you're used to reading more, if you're used to reading novels or works of fiction or things like that, you may find that this reading feels like it goes annoyingly slowly compared to the number of pages that you're reading. The first assignment might be 7 pages long. In a typical physics textbook or a math textbook, you've got to get used to encountering a sentence that I don't understand. It refers me to a figure that's 2 pages earlier, and then I've got to compare with an equation, which is on the next page. And then I've got to take out a piece of paper and write some stuff down and make sure that what is being claimed is actually true. And so even though the readings are not very long, you shouldn't expect that means you're just going to read through it like a novel. It won't sink in that way. In fact, it will make very little sense. Maybe the first chapter might, but the subsequent ones that have very detailed arguments in them won't make much sense. So give yourself a break. Expect that you're going to have to go back and check a passage when a claim is made and references something further back and you don't remember what that claim is referring to. You might have to go look it up earlier on in the book. So I said, Merman has written an excellent text appropriate for any Centre College student, which presents all of its arguments with great clarity. That's not to say it's an easy read. Even though every step in his arguments is relatively elementary, the arguments can be lengthy and require careful attention. In other words, when we're going through a detailed argument, it may be that everyone is willing to nod their head at every little step, every technical step that we make. But 15 steps later, you may have lost the entire thrust of the argument. So you really got to go back and familiarize yourself with those kind of arguments to understand in detail how the assumptions that are being made lead to the conclusions, which are going to be completely non-intuitive to you, things that you wouldn't have thought to have made up, unless you've understood something about relativity from before. Okay, class preparation, just, part of the preparation for class is making sure that you read those sections of the text beforehand. You're not going to be able to digest what the argument is just from the presentation that's given by me in class. I will try to summarize some of the points and maybe flesh out some ideas that aren't treated as well or sort of glossed over in the book. And it's a time also for you to ask questions and sometimes, even come up and present something at the board if it's confusing you so that we can discuss together. the reading responses are supposed to prompt you to think carefully about the reading. But again, it forces you to read purposefully, but equally importantly, it alerts me to things that I can address in the class the next day. Those reading responses are supposed to be due by 11:59 on the date that they're posted on. Okay, so if you're a really late night person, you need to get cracking early so you can get it in before midnight. That's so that when I wake up early the next morning, I can look at them, have time to look at them before I come to class and maybe integrate some of them into the material we talk about that day. Okay, a little bit more briefly here. Homework, we can talk more about homework, but if you're not used to doing homework that involves things that maybe a little bit of algebra or number kind of stuff, just do your best to make clear and beautiful solutions. Part of beauty is just being a neat person, and I know I'm not naturally a neat person, and so I have to work very hard at writing legibly, but make your arguments neat too. It's sometimes too easy when you're arguing something mathematically to have a sentence end in a half erased thing that's sort of been half scribbled out, and it makes the argument like, well, I'm not really sure what was intended there. So try your best to make the argument itself clear. One of the things that's addressed in the second paragraph is about collaboration. I certainly encourage you to collaborate with your classmates on homework. I think that helps a lot, and I don't want you to feel like you're doing something bad when you're doing that. I do ask in the syllabus that when you work on homework even with multiple people, it might be in a group of 4 or something like that, it's fine if you arrive at a solution, even based on the insight of one person in that group. Usually that's how it works, for everyone to base their solution off of that. But when you write down your solution, you should make sure that you own that argument. In other words, you understand every aspect of the argument, even if somebody else came up with the key idea that led to it. So I'm asking you in the syllabus to just cite who you worked on with the homework. If there's some major thing, I don't forbid people from searching things up online or looking in other books. So if you happen to find something useful or relevant online, certainly quote that source as well. Especially in the block term, it's so important that you come to class every day. So attendance will be taken every day. I'm required to take it every day and say exactly how many days you miss. Sometimes I get a little bit lax and I skip a day and forget to take attendance, but that won't be true in the block term. I'm really going to make sure everybody's here, because if somebody misses 2 days, that's a huge fraction of the term. Normally, there are lots of cases where people can have excused absences. Excused absences, the most predominant reason is for sports kinds of excuses, and that's somewhat mostly cut down to 0 during the block terms. But there are other occasions where you're visiting something, or occasionally a death in the family or something like that can be an occasion for an excused absence. So when they are excused and there's something you can let me know ahead of time, something's happening a week from today, just let me know ahead of time so I can plan and know that you're not going to be there that day. Illness, of course, is an excused absence. And if you can, let me know that you're ill that day. If you're so gravely ill that you can't let me know via email before class, that's fine. I understand that sometimes that happens, and you shouldn't force yourself at great personal expense to send an email to me. But it helps for me to know who to expect and not expect in class. My experience in Block 1 was that almost everyone was there every day. There were just a couple of people who missed for very specific reasons. And I'm assuming you're here because you're really invested in learning about this stuff. It's going to be a great, fun course. And tardiness is the same way. There are some people who, usually out of a class of maybe 30 or even 60 students in a double section of a class, there might be 1 student for who tardiness is a problem. And the little clause in there about a deduction from your grade for tardiness is for that 1 student. So this is not referring to most of you. I know almost everyone is not going to have a problem with that. And I imagine in this kind of class, it's not going to be a problem at all. Academic honesty, I'm not going to read through that, but I would recommend that you read the paragraph there. you know, I already talked about homeworks, and so the major other kind of thing that we're going to be doing is the exams. We're pretty spread out in here, so even if there were a temptation to glance at someone else's paper, it's probably not possible because you're so spread apart. So it may not apply as much. We won't be writing papers in here, but you know, of course, Dr. Kadavid probably will be having you write papers. So for us, it's not so important. And finally, if you need some accommodation due to disability, please let me know as soon as possible so that we can make sure that that is satisfactorily met. Dr. Brian Cusado is the new contact on campus for that, for those needs. So let him know, and then we can all connect and make sure that your needs are met. All right. I think that's the end of the syllabus. Any questions on it? Don't be intimidated by it if it contains a lot of stuff that you're not used to from classes that you might more normally take if you're a philosophy major or some other major around campus. I'm going to help you through it. The mathematics part of it is not going to be super intense, and it may sound like that's going to be a barrier at the beginning, but I don't intend it to be that way. Any questions, including the Zoom folks? All right, so the last thing I want to do today is just talk a little bit about something we're not going to spend any more time on during this course, but to set the context before we even address how Newton thinks about the universe, space and time in particular, but also motion is going to come in very strongly to Einstein's theory. I wanted to talk a little bit about the context, and you know, probably Dr. Kadavid knows more about the history of these kinds of ideas than I do, but this is just a very, very short context of how people thought about the Earth, the world, cosmology, from the ancient days and up until Newton. And as I said, I'm going to kind of treat Newton as, for more or less, for most of us, Newton is kind of the default point of view that we think of, or at least that's how I grew up thinking as a modern citizen. But it really is only because we're modern citizens. So here I'm going to talk very, very briefly about flat Earth kinds of models, where Earth is the center of the universe, or if your cosmological model. And then the switch from that to spherical Earth-centered models, and then the sun being the center of the universe, and then the work leading up to Galileo and Newton's kind of more or less models of the universe without a center to them. That's the more modern point of view. So let's start with the idea of flat Earth models, which you hear even in modern times about, but maybe they don't mean quite the same thing as they did in the ancient world. So a couple of things that are obvious to most residents of the ancient world. Not that this photo is of the ancient world, but I just wanted to show that if you look out in a place where you can actually see the horizon, of course the world isn't totally flat. There are ups and downs and hills and mountains and valleys, but it looks like, if I look far away, that on average it's flat. So that seems like a reasonable assumption, given that you don't know anything else besides that nice scenic view that you can see in places where there aren't too many trees. It just looks like it goes on for quite a distance. So that's something that people seem to take at face value in history. The other thing you spend an awful lot of time looking at as a member of the ancient world, and we don't spend enough time anymore, partly because of light pollution, but we just don't spend as much time outside at night as people once did. That's the stars. Besides looking at the Earth, you're looking out at the stars, or whatever you called them back then, and wondering what the nature of them was and what they told you about the total structure of the universe. And one of the first things you notice, you even notice this if you go out even once with an astronomer to look at stars, and that is that if you watch for a while, the stars all appear to rotate around one point in the sky. As the night goes on, they move around. They tend to rotate around where the North Star is. And if you're someone sitting here on Earth, this flat Earth, that may suggest that Well, those stars, they look like the little points of light pinned to something, tiny little points of light, and they're moving around. Maybe whatever they're pinned on is actually moving. And that's the edge of at least the known universe. And that's, well, we can't see my title here, but unfortunately, oops. This says a flat Earth model. Because of that screen share thing, we can't quite see it, at least here in the classroom. Flat Earth model with a dome-shaped firmament. The firmament, the idea was here that the intuitive picture that ancients, at least as far as I understand, took for the structure of the Earth and the universe is that the Earth is flat. It's surrounded by a dome. That dome has points of light in it, which are stars. And that dome rotates as time goes on with a flat Earth underneath it. And so that we can see different stars appearing above the horizon. Well, I guess different stars appearing as they rotate in and out of view from the point of view of someone on top of that. Of course, that, you know, this poor fellow here, or maybe he's a philosopher thinking, well, what's beyond the firmament, and peering his head through to see the nature of fundamental reality or something like that. But the idea is, at least the Earth, the universe that we observe involves this dome-shaped firmament and flat Earth. Where does the idea that the Earth is a sphere come from? And again, you know, it's natural to think of Earth as the center of the universe. It's all we ever really see around us. Well, there's a couple of things that if you're a really astute observer and you travel long distances, you know, long enough that you know, it would take maybe weeks of travel going south or something like this. So Aristotle observed that travelers going south see different stars, and the southern constellations rise higher above the horizon. So if you walk far enough south, you start to see stars, constellations that you can never see if you're a resident of the northern hemisphere. Now let's go back to that picture of the dome-shaped firmament. Oops. Anywhere I am on this presumably sort of disc-shaped Earth, anywhere I am, I can see the same stars that are up at any period of time, right? They may rotate out of view, but when they rotate out of view, they rotate out of view for everyone. And it doesn't matter where you are on that flat-shaped Earth. Whereas Aristotle is saying, well, look, if I walk in a certain direction, I start to see new stars that no one in the north can see. And that raises some questions about this model of the universe. Well, there's that picture again. Here's another piece of evidence that people mention. The shadow of Earth on the moon during a lunar eclipse. Lunar eclipse means the light from the sun is blocked from the Earth, so the Earth is in between the sun and the moon. Shadow of Earth is round. It's always round. And if the Earth were flat, this isn't a proof, but it seems like, you know, that flat-shaped disk would sometimes be at the wrong angle, and you might see sort of an ellipse or something that's sort of a squashed shadow rather than always a circular shadow. What's the shape of an object that always casts a circular shadow, no matter which direction the light is coming from? That's a sphere. And of course, there's other motivations for spheres. Spheres are sort of thought of in Greek times, as far as I understand, to be one of the most perfect shapes. They have lots of symmetries to them, and so people liked spheres. So there's there's other motivations, but this is a piece of evidence that shows that maybe the Earth isn't flat. Maybe it's a sphere. And so this is the genesis, at least as far as I understand the history of it. I'm no expert at it, of the idea of the Earth possibly being a sphere. And the models of Aristotle and Ptolemy, the idea is that these planets circle Earth, and the stars are included in that. The stars and the planets seem to move somewhat independently of each other, but the stars in this model are still imagined to be fixed to a firmament. So the firmament's like a spherical shell, and inside in this model is the spherical Earth, and the planets are sort of in between. And all of them move on circular orbits, at least the early kinds of models. Okay. Now, here's an interesting side question that maybe you've thought about before or maybe not, but it's an important question. If we're on a big sphere, how do I know how big the sphere is? The sphere's got to be pretty huge, because when I look out at the horizon, it looks more or less flat to me. I mean, it seemed plausible that we lived on a flat Earth. So now that it's a sphere, it's got to be a pretty big sphere. Well, here is the first measurement of the radius of Earth as a sphere by Eratosthenes. It says up there 200 BC. And it's quite a clever method. I wish I had come up with this method, because he was really paying attention to what people were telling him at this time about facts at the same time of year. So the idea was, at a certain time of year, there was a well in Syene that was known on a certain day of the year. The sun shone directly down into this well and cast no shadow onto the side in any direction. So it just hit perfectly on the bottom. At other times of the year, it would cast a shadow no matter what time of day. But at high noon, at this particular location in Syene, it was just perfectly aligned with that well. Well, so people got to talking. They talked to their friends up in Alexandria, where they had a big obelisk up there, which of course was oriented perfectly vertically as far as they could tell. And people up there said, you know, at that same exact day of the year, it's true that the shadow of this obelisk is as small as it possibly can be, but it doesn't go directly straight down like it does in the well in Syene. And so that seems to suggest that we're not living on a flat-shaped thing. And so here's the clever part, is if you just imagine a little bit of geometry. I'm not going to go through the math here, but what I can do is, on that day when there's no shadow in the well in Syene, what I can do is measure the angle that this shadow makes with the obelisk. That's being called alpha here in the diagram. And if I measure alpha, and I actually have a caravan of people who carefully measure the distance between Alexandria and Syene. They didn't do that in modern units. I think they used the unit of stadia, but it was convenient for people taking long trips. They measured the distance here in stadia, and using that angle, they could conclude what the radius of this sphere had to be in stadia. So in other words, how big it is to get halfway across the Earth, through the middle of the Earth, or the diameter of the Earth in terms of stadia. Pretty clever kind of method. There's lots of astronomical kinds of facts like that, although I wouldn't, since this is about Earth, it's not really an astronomical fact. But things like, well, how do we know what the mass of the moon is? It's not like we can weigh the moon. How do we know what the mass of Mars is? Or one of Jupiter's moons or something like that? Well, you have to be very, very creative, and people think for long times about these, and they come up with methods for how to figure out what those parameters are. Okay, then moving very quickly through history, as we know, at least for a while, people thought of the sun as the center of the universe, or the center of your cosmology. So where did sun-centered models come from? Well, the idea is, in these Earth-centered models, even though the stars behave very regularly, they seem to rotate around in circles as if they're attached to some big bowl, or a spherical shell that's surrounding you. The planets take sort of crazy motions around you. And they're not exactly circular motions, and so since circles are, one of the most perfect shapes, people had to work harder and harder to make the planetary motion seem plausible. And so the thing that simplified that was placing the sun at the center of all this spherical nesting that's been going on. So again, this is still a model here of Copernicus, 1543, that has that kind of firmament attitude to it, where surrounding all of this, and I think in this particular graphic here, so this outermost, which is supposed to be a circle or a sphere, this says stellarum something immobilis. So that means that that is a spherical shell of stars that are on the outside. People still didn't have the sense that stars were at different distances there. And then all the planets were moving on perfect circles centered around the sun. So Mercury, Venus, here's Earth right there. And that greatly simplified, the stars are no more or less simple in this model, but the planetary motion was greatly simplified. But it's somewhat, interesting from a historical perspective in that it places the Earth not at any particularly important position anymore. Okay, and there was an elaboration on that because it was known very quickly that the planets actually didn't move on perfect circles. They moved along ellipses, so Kepler's 3 laws improve upon that. If this were a physics class, I'd talk about more of them, but the first couple are pretty easy to understand. One is that the orbit of each planet is an ellipse. Now, a circle is a kind of ellipse that happens to have a focus right at the center of it, but an ellipse generally is something that's an elongated circle like this. And the sun is always going to be at one of the 2 foci of the planet. It's one focus there. What does the focus mean? Well, if you want to draw an ellipse, one way to do it is to put 2 tacks in a piece, permeable piece of paper, and tie a fixed length of string around them so that it's sort of loose. And then draw the curve that you can make by keeping that string taut all the way around. If you did that, these 2 tacks would be at the foci. And so the idea is, this is the motion of a planet, this elliptical orbit, the sun would be at one of these 2 foci. That's not going to be important for us in this course, but since it mentioned an ellipse, that's one intuitive way of defining it. The second law said something about, for a given planet, it sweeps out equal areas of these kind of triangles that have curvy sides to them. So it's like a weird piece of pizza or something like that. This area A1, the idea is in the same amount of time, this planet goes from here to here, sweeps out area A1. In that same amount of time, it goes from here to here at a later time in its orbit. And that sweeps out area A2. And the claim is by Kepler is that no matter what period of time you choose, if you compare that same period of time at 2 different parts of the orbit, the areas are the same in the same amount of time. And what that means is it's going more slowly out here by A2, right? Because it doesn't have to go as far to get the same area because it's got this huge dimension going in that direction. So the planets slow as they get farther from the sun, and then they speed up as they come in closer to the sun. So that's telling what one planet does. And the third law I won't dwell on. It tells us the relationship between how long it takes one planet to orbit the sun and how long it takes another planet to orbit the sun. And it relates to the size of the ellipse, in this case measured by what's called the semi-major axis. But I don't want to dwell on that because it's not going to be something we're really going to use as we go on. Okay, now finally, we're getting up to sort of what we would consider the modern age or the modern point of view, at least pre-Einstein, and that is Galileo and Newton's uncentered models. We've been talking about things that always had a definite center, first on us and then on the sun. Even in Kepler, everything happened relative to the sun. Now, Galileo comes along. Galileo, he was very talented in lots of different fields, but one of his great talents was building telescopes. He had superior optics compared to anything that had come before him, so he could see things that nobody else could see. And he reported, one of his most famous books or manuscripts that he wrote was called The Sidereal Messenger. I think it originally was in Italian, but this is a translation of it here. And it's really incredible to read, the kinds of front pages that they have here. The official title is The Sidereal Messenger, Unfolding Great and Marvelous Sights and Proposing Them to the Attention of Everyone, but especially Philosophers and Astronomers, being such as have been observed by Galileo Galilei, a gentleman of Florence, professor of mathematics in the University of Padua, with the aid of a telescope lately invented by him, respecting the moon's surface and an innumerable number of fixed stars, the Milky Way, nebula stars, and so on and so on and so on. So he talks about some, but that's just the front page there. I'm going to just go to one of the very important discoveries they relays in here, and there are several of them, but one of them concerns his observations of Jupiter. Let's just read a little bit from the translation of his manuscript. Then we'll look at some of his data and try to conclude what it's telling us. I was viewing the constellations of the heavens through a telescope. The planet Jupiter presented itself to my view. And as I had prepared for myself a very excellent instrument, I noticed a circumstance which I had never been able to notice before, owing to a want of power in my other telescope. Namely, that 3 little stars, small but very bright, were near the planet. And although I believe them to belong to the number of fixed stars, those means the stars that are in the firmament, yet they made me somewhat wonder, because they seemed to be arranged exactly in a straight line parallel to the ecliptic, and to be brighter than the rest of the stars, equal to them in magnitude. The position of them with reference to one another and to Jupiter was as follows, figure 1. So let's go to his figure 1. Here's the, I didn't put it all in here at once because I'm trying to put some drama in here. So here's his first night of observation. This big circle here is Jupiter. He's got a strong telescope, so he can actually see the size of Jupiter, right? It's not just a point of light like it is to our naked eyes anyways. Well, here's 2 of these stars that he can see on this particular night. Maybe he couldn't see any other ones. And, well, okay, the 3 of them seem to be in a straight line. That wouldn't be a great coincidence. But he goes out to observe the next night. And now there are 3 stars in Jupiter, and they're all still in a straight line. And as he goes on observing night after night, of course, you have to skip the nights that are cloudy. So he has little pieces of missing data in there. But, you know, the fixed stars don't do that. The fixed stars, everybody already knew Jupiter did its own crazy stuff, because now it's going around the sun, and the sun is the center of the universe. But these look like fixed stars, and they're certainly not fixed stars. They're not behaving like other planets. Other planets would be going all the way around and moving far from each other. They seem to be staying close, and they're always in a straight line. And of course, what he soon realizes is that what he is seeing is Jupiter. If we looked at it from a different direction, these are moons of Jupiter, and they're going around, not necessarily in perfectly circular orbits, but close to circular orbits like that. And yet we're viewing them from a point of view like this, where we're just seeing them go back and forth, and sometimes they disappear because they're behind Jupiter, or maybe they're in front of Jupiter, and Jupiter was so bright that you couldn't see it very well when it was in front of him. So sometimes there's 3, sometimes there's 2. Here was a night when he saw 4, so there are 4 big moons of Jupiter. And so the conclusion he comes to, which was actually, it seems mundane now, but it was mind-blowing at the time, because here's another center. We already know the sun is the center of a universe, but here's something else that's a center with something going around it. The moon seems to go around us, but you know, people didn't think that there were all these other centers. And so it began to be proposed. Giordano Bruno, I can't read the date there, proposed a cosmology without a firmament. In other words, all these stars that we thought of as being stuck in a big spherical shell are like our own sun in their own right, and they have their own planets going around them, and they're all sort of out there in the universe. So it's not like there's a center of the universe, but rather there are lots of centers of things going on, and it's unclear if any of them are the center of the universe. So gradually it became harder, more difficult to argue that the heavens were perfect in the sense of sort of Greek geometry, and this is the beginning of the point of view that Newton advanced. And so hopefully this goes to these questions now. I just wanted to end in the last couple of minutes, because I've been talking way too much today, ask you guys for just shout outs about your ideas of space and time, because normally if we were in another physics class, I might start talking about what Newton believed about space and time. And we have a lot of intuition about what Newton believed about space and time, believe it or not. When somebody says the word space, as you were growing up, you know, just say at the level of, you know, learning junior high school science, or, you know, whenever you became generally aware about the universe out there. Well, how do you think of space? It's tough to put it into words, but yeah.
I guess, like, we're just thinking of it as like an empty space where matter could be.
Yeah, so sometimes people say like it's a container, and matter's inside the container. Now, it's unclear where the edges of the container are, but it is some arena in which events can take place. Things can move through it, and it's sort of like the backdrop for a play of the universe or something like that. Right? Read.
Growing up, yeah, I was told the same thing. Like it's basically an empty void, but like growing up in school, we focused on a lot of what's in it, like specifically our solar system.
Mm-hmm.
So to me, it seemed like it was pretty like dense and like full of matter, but it's not the case.
Yeah, it is rather empty. And it's a rather kind of, if you conceive of it that way, it's a very strange kind of object. It's not like anything else. Everything you point to, for the most part, is something that's in space. But to call space a thing, it's not like any other thing that you name. So it is somewhat interesting that way. And I'm sure because of the book we're going to read in Dr. Kadavid's class, we'll get into that with the Leibniz-Clark correspondence, talking about different ways to conceive of the universe, but maybe it's a little bit suspicious that space is its own kind of thing, and we shouldn't believe in it in as much as a thing. Okay, what about, okay, here's a question. It's challenging. If someone stops you on the street and says, "What is time?" That's a tough question. But we talk about it. I mean, it's a noun we use. There is time. Time has property. Time passes. Anybody, I think I wouldn't know how to answer this question, but I'm challenging you guys, your conception of time. Because these are the concepts we're going to be challenging in both classes throughout this term.
I have an idea.
Okay, hold on for just a second. Who is that? Was that Muchiri? No, was that?
Yeah.
That was Muchiri? Okay, hold on for just a second. Someone was responding in class, and I'm going to try to repeat what the response was here, and then I'll get to you.
Okay.
Okay, go ahead. Yeah, so the answer was, it's not exactly clear what time is, but it is sort of a parameterization, a way of naming things that happen in succession. They have a certain order, but it's difficult to say exactly what it is. Muchiri?
I think it is that which stops events from happening together at the same time. That which stops events from happening together.
I'm sorry, did you say that which stops them? S-T-O-P?
I'm saying time to me is like that which stops events from happening simultaneously.
I think he said that's which stops events from happening simultaneously. And I'm not really sure I understood that, but maybe I wasn't hearing you correctly.
Can I answer?
Absolutely, Royce, take it away.
Time is the measurement of change.
Okay, that's a kind of interesting point of view. So that's saying time is a measurement and that there is something called change. We're all familiar with the idea of change and that events happen. It seems like, ordinary everyday objects move around in the world, and time somehow is a measurement of how rapidly or the degree to which things change. We might connect with that in the philosophy course. We'll have to see. Anything else? Okay. How about the relationship between space and time? There's no right or wrong answers here, but I'm just trying to tease out what the intuitions we bring into the course are. Because Einstein has a very definite idea of a relationship between space and time. In fact, they're really not different from each other in a very fundamental sense. But I wonder, what about Newton? Or your intuition that you're bringing into the course? Yes. Yeah, so the comment was that it's interesting that we can measure distances in space using time units, and we'll certainly get into that in this course. For example, measuring very large distances using units of light years. And so it seems like there is a connection there. The connection is partly just motion and things moving at a uniform rate. But it is interesting that we can use one to kind of almost define how to measure the other one. Okay, if there's no other comments, I think I'm going to leave it there. Again, this historical kind of perspective isn't going to feed into the main theme of this course, but I thought it could set the stage because we're right up to the time of the ideas of Newton, and we're going to take those ideas as kind of the leaping off point for going into Einstein. So we'll put them into words, but we're not going to dwell on the ideas of Newton, and we will, I think, in Dr. Katavid's course quite a bit more, and we can certainly make any connections we want in here as they arise. All right, thank you very much for your attention. We're going to get into chapter 1 tomorrow, so your homework for tonight is the first section of reading in here, doing those posts, and certainly email me if you're having trouble connecting. You should all be available to see that website. I have to give you permission, but I think I gave everyone on the list permission. So if you're having trouble seeing it, that's fine. We'll get the kinks worked out, but let me know via email that you couldn't see it or any other technical problems that you have. And if anybody wants to stay after and ask questions or express other concerns, feel free. I'm going to leave the Zoom on for a second, but if not, I'll see you in Dr. Katavid's class meeting. Yes.
So if one were looking for more calculus-based version of this class, or a more calculus-based book,
I can certainly recommend one, and I don't know that the library owns the most recent edition of it, but they do own probably the prior edition to it, and it's called Wheeler and Taylor are the authors, like as in a car wheel, wheel E-R, and T-A-Y-L-O-R, and it's called Space-Time Physics. Space-time is one word. And that's like a calculus-based book. It's used quite a bit at the undergraduate level. I will say, you know, I like it. It goes into great detail. It's also very sort of quirky in the way it's written, which can be very appealing to certain people. But what makes it quirky also makes it less sequentially organized. And so you have to be a really dedicated reader to go through all the details. But I would check that out and see if that's appealing to you. There are lots of extra books. I didn't put any supplemental or recommended reading on just because I didn't want people to feel compelled to buy books that we weren't going to be normally referencing in the course. But I can even, you know, get a list of 5 or 6 kinds of books that would be at the undergraduate level on the topics that we're talking about, and they won't hesitate to use the language of vectors and calculus and all that kinds of stuff. What year are you?
I'm a sophomore.
Sophomore. So what are you going to declare for a major, do you think?